impressed me. Of course, the first thing that impressed me was the success of the Bohr orbit theory. I went to Cambridge as a research student, knowing nothing at all of the Bohr orbit theory, considering atoms to be something very mysterious and quite beyond the range of ordinary dynamical laws. And then it was a revelation to me to hear about the atom of Rutherford and Bohr. Rutherford has set up the basic model of the atom having a central positive nucleus with electrons moving around it. And then Bohr had found out laws governing the motions of the electrons. He set up his orbit theory, according to which an electron moving in an atom is subject to the ordinary classical laws corresponding to its charge and the field that it is moving through. The ordinary classical laws, except for that part of the force on the electron which is associated with the emission of radiation. That part of the force, which is just a small part, has to be cut out. Then the remaining force gives a stable orbit for the motion of the electron. That answered one of the most mysterious questions which people had been bothering about previously. How was it that an atom could have any stability? Why didn't the electrons all fall into the central nucleus, emitting their energy in the form of radiation? Bohr said that this radiation process just didn't take place. You have to neglect that part of the force in the motion of the electrons. And then you have a possibility of stable orbits. And further, the stable orbits have to be subjected to certain quantum conditions, certain new conditions quite foreign to anything which we have in classical mechanics. These new conditions involve a Planck's constant. If we have an orbit satisfying these conditions, then the electron in such an orbit can make a jump to another orbit, and when it makes this jump, it emits or absorbs a quantum of radiation, according to whether the jump is to a state of lower energy or higher energy. And the frequency of the radiation is connected with the energy difference by that famous equation, difference in energy equals h times nu. These ideas of Bohr were completely strange to anyone who had just been brought up on classical mechanics, but one had to accept them because they were so successful in describing the spectra of simple atoms. By simple atoms, I mean atoms in which there is just one electron playing a major role in fixing the states of energy. So that it applies to the hydrogen atom, which has only one electron altogether, and also to the alkali elements, where there is just a number of electrons in closed shells and one outer electron, which is moving about and doing the interesting things. This Bohr orbit theory was a complete revelation to me, and of course I proceeded to work on it, and I accepted Bohr orbits just as something which was fundamental in nature. That was rather a mistake on my part, because it gave me too narrow an outlook. I proceeded to study the Bohr orbits following the theory which had been given by Sommerfeld. Sommerfeld had obtained more general equations for quantizing the Bohr orbits than the ones originally given by Bohr. And Sommerfeld's conditions were expressed in terms of the Hamiltonian variables, coordinates and momenta. Now you first learn Newton's laws of motion in terms of positions and velocities of particles, and then you learn about a more general formulation of the equations, the Lagrangian formulation, where you have quite general dynamical coordinates, coordinates which are any functions of the positions of the particles, and then you have the velocities corresponding to those coordinates. Now, Hamilton, 100 years previously, had set up another form of dynamics in which the coordinates are replaced by momentum variables. Now, you might think that that's not an important change, but it led to greater symmetry and beauty in the equations. And Hamilton pursued this line of investigation just because he was striving for mathematical beauty. I believe it shows very strongly the genius of Hamilton, that he was able to follow through a line of work whose importance was not made evident until 100 years later. I don't think there's any other such example in the history of physics. Well, I studied the Hamiltonian theory of dynamics because it was found to be the most useful one for examining the Bohr orbits, as Sommerfeld had shown. I studied this theory on my own, reading the book Whittaker's Analytical Dynamics, which is a very good book on this subject, and I learned about the transformations of the Hamiltonian variables and the invariance of those transformations, and a whole mathematical theory attached to it. I learned this up without, at the time, realizing whether it would be important or not, but simply that it was related to things that were important. The real difficulties of the Bohr orbit theory occurred when one tried to consider the interaction of two of these orbits. If you have the atom of helium, for instance. Now, the spectrum of helium was very peculiar. There seemed to be two different spectra associated to two different energy levels, and the transitions between those two energy levels were extremely rare. That was a phenomenon which one just could not explain at all. One talked about two kinds of helium, parahelium and orthohelium, and one had no explanation for them. This was the situation in which I first studied in Cambridge for 2 years, puzzling over the difficulties and the limitations of the Bohr theory, and not making any success. The real breakthrough was done by Heisenberg in 1925. Heisenberg came to Cambridge in June of that year and gave a lecture there. The lecture was mainly on the anomalous Zeeman effect, but he did refer at the end of his lecture to the new ideas associated with his matrix mechanics, which were just beginning to form in his mind at the time. Now, I'm afraid I was too tired to follow just what Heisenberg was saying at the time. It was very late in the evening and at the end of a complicated lecture, and sorry I didn't pay the importance to those ideas that I should have done. But that lecture of Heisenberg did not affect me at all. It was just 2 months later that I received a copy of the proofs of Heisenberg's first paper on quantum mechanics. People didn't have preprints in those days, but they did circulate a few copies of the proofs to their friends. And Heisenberg has sent a copy of the proofs to R.H. Fowler, who was my supervisor at the time. And Fowler passed it on to me and asked me what I thought of it. This was Heisenberg's first paper on quantum mechanics. I looked through it and I didn't think very much of it. I suppose I looked through it too hurriedly and I put it aside and went back to it again after about 2 weeks. And suddenly it got revealed to me, don't quite know how, that this was really important work and that it was really something new which could provide a solution to the whole of the problems of quantum mechanics. The way Heisenberg had proceeded was like this. He said that we had been working all this time with Bohr orbits, but the Bohr orbits were really not very physical things. One could not observe the variables that come into the description of the Bohr orbits. One couldn't observe the electrons in the stationary states at all. The things that one could observe are always associated with two states. The things that one could observe are associated with the emission or absorption of a quantum of radiation. And such radiative processes were always connected with two states instead of one state. And Heisenberg's genius enabled him to see that one ought to concentrate one's attention on things which are closely connected with what one can observe. The things which one can observe, being each related to two states, are expressed naturally as a matrix array of numbers. A set of numbers like this. And Heisenberg proposed that one should consider the whole set of numbers together. When Heisenberg first got this idea, he did not know anything about matrices at all. He'd never heard of them. But he was led to construct these arrays of quantities simply from the physical idea that one should work with quantities closely connected with observation. Then Heisenberg thought of taking the whole matrix of quantities together and handling these matrices as individual things. One would add matrices in a trivial way. One would multiply them according to the law of matrix multiplication, which was also suggested by the physics. One didn't need to have much mathematical knowledge to think of that law. So Heisenberg was led to think of these matrices as being able to replace the dynamical variables of mechanics. And he set up in that way his matrix mechanics. The main feature of this matrix mechanics is that if you have two matrices, U and V, and multiply them in that order, the result is not the same as V times U multiplied in that order. When Heisenberg first noticed this, I heard that he was extremely perturbed by it. You see, it was so foreign to any idea which physicists had had previously. Positions and velocities were certainly ordinary numbers and certainly satisfied ordinary algebra. How could one replace them by things which did not satisfy ordinary algebra? But still, there was no escaping from this at all. Heisenberg just had to get used to the idea. When I read Heisenberg's paper the second time, I picked on this non-commutation as the important feature. It seemed to me that this was really the prime difference between the new mechanics and the old mechanics, and that what one had to do was to take the old mechanics of Newton, or maybe in the Lagrangian or Hamiltonian form, and modify it in some way so as to bring in the non-commutation. You see, I wasn't disturbed by the non-commutation in the way that Heisenberg was. The person who originates a new idea is really not in the best position to follow it up, because he's so scared that something will turn up which will knock the whole idea on the head. And I suppose that was really why Heisenberg was worrying about this non-commutation. He said that with this non-commutation, it seems that I should have to abandon the whole idea. Now, someone who does not originate the new idea doesn't have that kind of disturbance and is better able to follow up the consequences of an innovation of this type. Well, I proceeded to think intensively about how one could modify the laws of mechanics so as to fit them in with this non-commutation. At that time I was a research student in Cambridge and was just concentrating all my efforts on solving these basic problems. I used to spend most of my time on this work, but on Sundays I had the habit of taking it as a day of relaxation and taking a long walk in the country. And during those long walks I would just rather forget about my work and maybe just keep it faintly in the back of my mind and essentially have a time of relaxation. It was during one of these Sunday walks, either the end of September or beginning of October, I'm not quite sure which Sunday it was, in 1925, that it occurred to me that there was really a great similarity between the quantity uv minus vu, the commutator, and the Poisson bracket, which I had been reading about previously when I had been studying the Hamiltonian, the general Hamiltonian theory in Whittaker's book. Would it be possible to say that this quantity just has to take the place of the Poisson bracket? It was a very exciting idea to me, and the difficulty was that I didn't remember very well what the Poisson bracket was. At the time that I had been studying it, I didn't know it would be very important. There was another kind of bracket expression also occurring in Whittaker's study of the general transformation theory of the Hamiltonian equations, the Lagrange bracket. And I was rather confused between the two. I wasn't sure of just what the definition of a Poisson bracket was, and without having the precise definition available, I couldn't make the detailed comparison between the Poisson bracket and this commutator. Of course, I was very anxious to settle this question, so I rushed home, tried to look up what a Poisson bracket was, but none of the books that I had at home was sufficiently advanced to mention Poisson brackets at all, nor were the lecture notes which I had. It was a Sunday, all the libraries were closed, so I had to wait till the following Monday morning and spend a rather uncertain night wondering whether this theory would turn out to be right or not. I think before the end of the night I had acquired considerable confidence that it was all right, but it was necessary for me to go to the library on a Monday morning, look up Whittaker's book, see just what the definition of a Poisson bracket was, and see that they really do correspond. The definition, as you probably know, is Poisson bracket written U times V with square brackets is equal to the sum of all over all the degrees of freedom du by dqr dv by dpr minus du by dpr dv by dqr. The q's and the p's being the Hamiltonian coordinates and their corresponding momenta. In Whittaker's book, he uses a different notation, round brackets for the Poisson bracket, and square brackets for the Lagrange bracket. Now, the Lagrange bracket is of no importance at all for quantum theory. We only want the Poisson bracket, and I did not like to use round brackets for something which is antisymmetrical between the two quantities that are mentioned in it. That is quite different from what we have in vector analysis, where we have the round bracket for the scalar product and the square bracket for the vector product of two vectors. So I changed Whittaker's notation and introduced the square bracket as being more suitable for something which is antisymmetrical. And since then everyone has followed that notation and used the square bracket for the Poisson bracket. Well, I checked in that way that this quantity really does have analogous properties to uv minus vu, and in fact the relationship between them is so close that we can put the Poisson bracket equal to uv minus vu with a numerical coefficient I times crossed h. Crossed h is Planck's constant over 2 pi. This is the start of my work on quantum mechanics. This turned out to be an equation of general applicability, and it provides a way of passing from any classical mechanics, from the classical mechanics of any dynamical system, when expressed in the Hamiltonian form, to the corresponding theory in terms of the new mechanics of Heisenberg. Heisenberg, of course, was continuing to work on this theory, and he was assisted by his professor, Max Born, and by a fellow student at Göttingen, Jordan, and they obtained equivalent results to mine, but they didn't have the single general step of making the commutator correspond to the Poisson bracket. They first worked out the complete theory for a system of 1 degree of freedom, and then assumed that variables associated with different degrees of freedom commute with each other, the natural assumption to make, and that leads then to this relationship. On the basis of this connection, one has equations of motion for any dynamical variable u. The classical theory in the Hamiltonian form says that du by dt equals the Poisson bracket of u with this capital H. This capital H, called the Hamiltonian, is the total energy expressed in the Hamiltonian variables q and p. And this leads at once to the equation of motion in the new mechanics, IH du by dt equals UH minus HU. We had then a general equation of motion applicable to any system in quantum mechanics if we know the corresponding theory in classical mechanics expressed in the Hamiltonian form. I wrote up this work and also applied it to the hydrogen atom to work out the energy levels there. And then I heard about another form of quantum mechanics which had been discovered independently by Schrödinger. I saw about it in the literature, and Heisenberg wrote me a letter asking me, what do you think of this theory of Schrödinger? At first I felt rather hostile to Schrödinger. The reason for that was that I was very well satisfied with this theory of Heisenberg developed in this way. It seemed to me that that would really provide the key to the understanding of the whole of the mechanics of the atom. Now, if we have a basis of something which we can work on to develop quantum mechanics, why go back to the pre-quantum mechanics stage and look for another solution to the problem? That was what I felt at the time, and I just did not want to go back and consider the possibility anew, neglecting all this work of Heisenberg and trying to get an alternative solution to the problem. However, the Schrödinger theory was examined by other people, and they soon found out that it was equivalent to the Heisenberg theory. It didn't mean that we had to abandon any of the ideas of the Heisenberg theory. We just had to supplement those ideas with some further ideas. And the main new idea which is brought in is the idea of the wave function, which represents an atomic state. Here we are working with matrix elements. We're working with matrices composed of matrix elements, each associated with two atomic states. The Schrödinger form of the theory provides us with a wave function psi, a function of the coordinates of a particle, x1, x2, x3, and time, which is associated with a single state, something which is not directly connected to anything in the Heisenberg picture. This psi is subject to a wave equation. We have the wave equation where certain operators operating on psi produce zero. I might mention as a historical point, which is perhaps not so well known, Schrödinger was led to his wave equation from a study of some work of de Broglie, published in 1924, that is to say, before Heisenberg. De Broglie had set up waves associated with free particles. He set up this wave equation, d2 over c squared dt squared minus d2 by dx1 squared minus d2 by dx2 squared minus d2 by dx3 squared plus m squared c squared over h squared psi equals naught. And he showed that the waves associated with the solution to this equation can be connected with a particle having momenta and momentum components and energy given by these equations. PR times psi is the same as minus IH d psi by dxr, and the energy, say, W psi equals IH d psi by dt. This connection between the waves and the particle is relativistic. It holds in all Lorentz frames of reference, and that is very interesting mathematically. I'd read about de Broglie's work, but it seemed to me to be purely an interesting bit of mathematics without any application to physics. How could there be any physical connection between waves and particles? However, Schrödinger had taken this work of de Broglie seriously, and he had set about trying to generalize this equation to make it apply to a charged particle moving in an electromagnetic field. And he succeeded in getting such an equation. It's just this equation with some further terms coming in involving the electromagnetic potentials. Now, having got such an equation which looked very beautiful, Schrödinger proceeded to apply it to the hydrogen atom, to the motion of an electron in the field of the proton. And he worked out the energy levels for the hydrogen atom, and he got the wrong result. The reason why he got the wrong result was, as we now know, that his equation did not take into account the spin of the electron. The spin of the electron was something which just about then experimental people were beginning to speculate about. It hadn't been established at all, and Schrödinger had probably never heard of the spin of the electron. At any rate, Schrödinger explained to me many years later how he was extremely dejected when he found that his beautiful equation did not give the right answer. He was so dejected that he thought the whole thing was wrong, useless, and he cast it aside. And it was only something like 3 months later that he had recovered from his depression sufficiently to go back and look at the equations again. And then he saw that in the non-relativistic approximation, his equations gave energy levels in agreement with the observed spectrum of hydrogen. And he published then his first paper on the new wave mechanics in a non-relativistic form. So if you look up the published papers of that time, you will see that all the early papers of Schrödinger are in the non-relativistic form. And that was not because Schrödinger was not appreciative of the importance of relativity, but simply that he saw that trying to take these relativistic corrections into account led him to energy levels which were not in agreement with observation, and he did not have the necessary boldness to publish papers giving results in disagreement with observation. I think there's a moral to that story, that if your theory is really a very beautiful one, and it doesn't altogether agree with observation, you ought still to publish it, because it may very well be that the disagreement with observation comes from some factor which is not properly understood at the time and which will be explained later. And you shouldn't be too depressed and abandon the whole thing because of such a disagreement. Well, this wave equation involving d2 by dt squared, which was abandoned by Schrödinger, was resurrected about 2 years later by Klein and Gordon, and is now known as the Klein-Gordon equation, although it had been discovered by Schrödinger quite a while previously, and was discovered by him actually before his discovery of the non-relativistic form of the equation. Well, that is how the Schrödinger form of quantum mechanics appeared. Schrödinger was working quite independently of Heisenberg. Heisenberg and Schrödinger could, each of them by himself, have discovered quantum mechanics if the other one had never existed. Just an accident of history that they were both led to their discoveries at about the same time. The use of the Schrödinger theory was to supplement the Heisenberg theory and give us something appearing in the equations corresponding to a single state. The matrices of the Heisenberg theory correspond in the Schrödinger form to operators, linear operators, which one can apply to a wave function psi and get another wave function from it. And the connection between the Schrödinger theory and the Heisenberg theory comes from the fact that with the momentum variables interpreted in this way, we get commutation relations between the momentum variables and the coordinates just the same as those of the Heisenberg theory. These relations are QR, QS minus QS, QR equals naught, PR, PS minus PS, PR equals naught, QR, PS minus PS, QR equals IH, delta RS. This means naught when R differs from S and 1 when R equals S. Are the basic commutation relations which we have in the Heisenberg matrix mechanics when we connect the commutator with the Poisson bracket. And they are also the equations which follow from the Schrödinger theory when the p's are understood as operators of differentiation on the wave function in accordance with these equations here. And that is why the two theories of Heisenberg and Schrödinger are really mathematically equivalent. Well, we then had a general basis for quantum mechanics, and I was concentrating my attention on it, and I found out that the quantum mechanics is in many respects more general than the classical mechanics. Classical mechanics, as we deduce it from Newton's laws, is expressed in terms of P's and Q's, the basic variables of the Hamiltonian formulation. Now, we can set up a scheme of equations in quantum mechanics in which our variables are not just P's and Q's, are not P's and Q's satisfying these relations. We could start with any dynamical variables satisfying definite commutation relations which are consistent with each other. We have to have them consistent, that's all that we really need. If we have any dynamical variables satisfying consistent commutation relations, and then if we take any Hamiltonian h, a function of these variables, satisfying a certain condition of reality, we can use that h to give us equations of motion of the Hamiltonian form there. Reasonable, consistent equations of motion. And in that way, we can discuss dynamical systems in quantum mechanics which do not have a classical analog. There are several examples of that which I might mention. One of these is that we might take as our basic variables the variables describing the spin of some particle. If we take the three components of spin, S1, S2, S3, then they satisfy commutation relations similar to the commutation relations of an orbital angular momentum. That is to say, S1, S2 minus S2, S1 equals IH, S3, and two similar relations which we get by making cyclic permutation of the suffixes 1, 2, and 3. We can set up a theory where we have a particle with spin and represent the spin by these variables here satisfying these commutation relations, and put the spin variables together with the coordinates and momentum variables of the particle into our Hamiltonian and get reasonable equations of motion which we can work with. Now these S's are perhaps not expressible in terms of Q's and P's at all. We have some basic variables here not expressible in terms of Q's and P's, and thus we get a generalization of the original form. Of course, sometimes these S's can be expressed in terms of Q's and P's, namely when they do describe the orbital angular momentum of some particle. But it may be that these S's describe a spin of a half a quantum, and then it is quite impossible to express them in terms of Q's and P's. That is one way in which we can generalize the original formalism, and that is rather similar to what the high-energy physicists are doing nowadays when they introduce the variables associated with some group to describe the internal degrees of freedom of the new particles which they are continually discovering. There may be some group, SU2, SU3, SU6, which turns out to come into the classification of the new particles, and then the elements of that group will be things which we can treat like dynamical variables, and all that we need to know is the commutation relations between those elements. They are provided if we know the group, and then we can proceed to set up a Hamiltonian involving those group elements and get equations of motion. That is one way in which this theory was developed. Another way arises when we consider a dynamical system containing many similar particles. For example, a dynamical system containing many electrons. Then we have our wave function psi, using the Schrödinger formalism, involving variables x1, xr1, r stands for the suffix 1, 2, 3 for the three directions of space, xr2, xr3, and so on for the various particles. Now, it's possible to consider a wave function which is symmetrical between those particles, or alternatively, a wave function which is antisymmetrical. Or more generally, we can introduce permutation operators which apply to the various particles. Interchanging 1 and 2 is an example of a permutation operator. We may introduce such permutation operators into our dynamical theory, and there we have some new dynamical variables quite foreign to any dynamical variables which occur in classical mechanics. This proved very fruitful for understanding relationships which arise for an atomic system containing several electrons, and it provided a ready explanation of the spectrum of helium. The orthohelium and the power helium are just associated with the different symmetry properties of psi with respect to the two electron variables. Then another important development was concerned with the introduction of operators of absorption and emission of particles. We don't have to suppose that the number of particles is conserved in quantum mechanics. We may consider the operator of creation of a new particle into a certain state, or the operator of destruction of a particle in a certain state. There again we have some new dynamical variables quite foreign to anything which we have in classical mechanics. This development led to the possibility of setting up a quantum mechanics associated with fields. Well, the result of all this work was to set up a very powerful scheme of equations in which we could make transformations of our dynamical variables a good deal more general than the transformations of the classical Hamiltonian variables which are dealt with in Whittaker's book. We had all these equations, and the question arises, how was one to interpret these equations? That was an unusual situation in physics, to have equations before you know how to interpret them. People guessed at the interpretation in certain simple cases and gradually generalized these guesses until a general interpretation was found. One could set up fairly easily an expression for the average value of any dynamical variable associated with a particular state. Now, if you know the average value of u, and you also know the average value of any power of u, u squared, u cubed, and so on, you have enough information to be able to determine the probability of u having any value. So that the interpretation of these equations led us to a formula for the probability of a dynamical variable having a specified value. This probability was expressed in terms of the square of the modulus of the wave function. If we take mod psi squared, and psi is a function of x1, x2, x3, that will, when it's suitably normalized, give you the probability of x1, x2, x3 having certain values. And we could transform psi to other dynamical variables and calculate the probability of those other dynamical variables having specified values. The interpretation thus combined with the general transformation theory to enable us to work out probabilities of any dynamical variables, provided, of course, that those dynamical variables commute with each other. You can't work out the probability of a certain p having a value and the corresponding q having a value because they don't commute. You see that the interpretation involves probabilities and does not enable you to assert that a certain quantity has a certain value when there are given initial conditions. That was a big departure from the ideas of classical mechanics, where we always had determinism. On given initial conditions, we could, with certainty, work out the conditions at a later time. This uncertainty associated with probabilities was something which disturbed many physicists. I suppose it disturbed us all to begin with very much, and people tried hard to get away from it, but without any success. And it is now accepted that, well, it is now certain that this kind of probability interpretation is the best that one can do with the existing formalism of quantum mechanics. There was a big discussion between Bohr and Einstein. Einstein did not accept a physical theory which would only give probabilities. As he expressed it, the good Lord does not play with dice. Bohr was the champion of the probability interpretation of quantum mechanics, and they went on arguing for the rest of Einstein's life on this subject. With regard to this argument, one must say that Bohr was correct with regard to the existing quantum mechanics, but I'm not sure that Bohr is ultimately correct, because the existing quantum mechanics should not be considered as the final solution. The reason for that is that, as I shall be talking about in some of the later lectures, it does lead to some fundamental difficulties. Difficulties which seem to me just as bad as the difficulties that one had when one was trying to discuss the interaction of Bohr orbits. I think there are very few physicists alive at the present time who remember the difficulties we had in trying to consider the interaction of Bohr orbits. They've rather forgotten that situation, and they are perhaps too complacent about accepting the present quantum mechanics. I feel pretty sure that the present quantum mechanics is not the final answer. The reason being because of these very basic difficulties. The final answer will very likely involve a change in our basic ways of thinking, just about as drastic as the change from Bohr orbits to the quantum mechanics of Heisenberg and Schrödinger. And when we do make such a basic change, well, who can say what would happen to determinism? We might have a return to the classical determinism at the expense of giving up some very fundamental, generally accepted idea which has never been challenged up to the present. We cannot have a return, simply a return to the previous classical theory. Science, physics doesn't advance backwards like that. But we may have a return to determinism at the expense of some very drastic new change, and then people may feel that perhaps Einstein was really basically right in his discussion with Bohr. And we'll stop there for today.
Thank you. This is a record to the Williams to the questions or anyone has a question.
Nobody.
We feel that the Banish Hoffman's book, A Strange Story of the Quantum Spirit of the Early Days of Quantum Mechanics.
I don't think I know the book well enough, but from the work of Banish Hoffman, I think that he looks at things from the point of view of the pure mathematician rather than the physicist. I rather think that he would put the emphasis in a different way from the way I would put it, but I don't happen to know that book. Or I've forgotten it if I have read it in the past. How long ago did it appear?
1950.
1950. Yes.
Could your, the fact that you weren't bothered by the non-commutation has something to do with the fact that you started off as Benjamin?
I think that the only answer to that is no. It bothered Heisenberg because he was afraid that his whole theory might collapse. And that is rather a terrible thing when you've got a wonderful idea. You want to avoid that at all costs. What did Einstein repudiate?
I think Einstein repudiated an attempt to make a unified field theory of electromagnetism and gravity. And that took the quantum mechanics, which it is possible, not to the rather than relativity.
Well, I feel that it's impossible to answer this question until the new improved quantum mechanics is discovered. A new improved theory which will differ from the present theory as much as the present theory differs from the Bohr theory.
Professor Dirac, when you write down the amplitude squared as a wave function and interpret it as a probability, it's usually stated that this, while applying an element of coordinate space, is the probability for finding the particle in that space. It's always puzzled me. I would wish you would comment on this. In the case where psi itself has a non-trivial time dependence, would this be interpreted as a probability per unit time in making this statement? In other words,
Not a probability per unit time, but the probability varying with the time. You can look upon that probability as a certain density, and that varies with the time.
And the time enters only as a parameter. In other words,
Yes.
The measurement is to be made in infinite time.
That is so, yes. Yes. There is no symmetry between space and time at this stage.
What is your opinion on renormalization method? Do you think that a new quantum theory would have the same way of quantum probability?
Renormalization is a sensible physical idea if the renormalization factor is small, or at any rate if it is just an ordinary number. But a renormalization factor that is infinitely great is just nonsense. And any theory which leads to such a renormalization factor is wrong. It's just as though you were trying to construct a theory of interacting Bohr orbits and got some equations which looked all right in a certain sense and then led to an infinity when you examine them a bit more closely. It's the sort of thing you would expect to have, and the proper conclusion to draw is that your basic ideas are wrong. You may wonder, why is it that the renormalization has had such a considerable success? I feel that the answer to that is a fluke, just like the Bohr theory had considerable success when applied to one-electron problems, even though it was basically a wrong theory.
Thank you very much. This is a record wire at the same time. I think it's 3 long magnetic long.
Come on. Do it. Do it. Do it. Do it.
Do it.
Do it.
Do it!
Who is doing it? Do it.
Do it.
All of it.
Do it.
Come on! Do it now! I will do the rest.